So one of your linear algebra homework problems involves a fairly big matrix like the one I have here. It's a 4x5 matrix. The linear transformation it defines would have a domain that's 5-dimensional space and codomain that's 4-dimensional space. And one thing you want to find is, well, parametric description, parametric vector form of the image and kernel like usual. And we can do those in the usual ways. But more importantly, now related to new content that you've been learning in the lectures, if you kept up, is to relate this to the idea of linear independence and basis for subspaces. If we row reduce A and put the answer in matrix form, so we can, the matrix form just makes the output look nicer. That's all it does. I've got to enter A, memory there. See, there's a matrix not in matrix form. So it looks nicer to have that in matrix form. There's the row reduced form of A if it's in matrix form. Let's first imagine, let's go ahead and first find a basis for the kernel. So for this example that's in Mathematica, you maybe didn't write that down. I'll show you at the end of class if you want to still write it down. A basis for the kernel of the corresponding linear transformation is going to be related to what you've done before, trying to write the kernel in parametric vector form based on the free variables. Now, I didn't make this an augmented matrix. I didn't make it a column of zeros to begin with. You could imagine doing that. And again, when you do row operations, that column of zeros does not get affected. But it's good to imagine, and maybe even good to write by hand, that other column of zeros, like with the dashed line just to the left of it, to remind yourself, okay, I've got 5 variables here, x1, x2, x3, x4, and x5 to correspond to the 5 columns. Because the leading ones are in the first, second, and fifth columns, the free variables will be in the third and fourth, x3 and x4. And you need to imagine bringing them to the other side of the equation. So for example, x1 is 3 times x3 minus 5 times x4 when I bring those to the other side of the equation. x2 is negative 2 times x3 plus x4. x3 and x4 are free variables, so they just equal themselves. x5 evidently is 0 because you don't see any free variables, any other non-zero numbers there. x5 must be 0 because you got a 1, and then with an augmented matrix you'd have a 0 over there. So can I write down a basis from that? It's a little tricky. First, think about the free variable x3. I know x5 is 0. I know x4 is sort of independent from x3, so x4 is 0. x3 is itself, so this is going to be a 1. x1 is, in terms of x3, it's 3 times x3. So the first component will be a 3. And x2 will be negative 2 times x3. So the second component will be a negative 2. That's a single vector that in the parametric vector form of the kernel would be multiplied by x3. But when I write a basis, I don't want to have any variables in it. In fact, since there's 2 free variables, there are going to be 2 vectors that I write down. This first one, again, would be have an x3 in front of it in the parametric vector form of the solution set. The other one has an x4 in front of it. Still x5 is 0, x4 is itself, so you put a 1 there. x3 is independent of x4, so you put a 0 there. x1 is negative 5 times x4, so I put a negative 5 in the first spot. And x2 is 1 times x4, so I put a 1 in this spot. These 2 vectors form a basis for the kernel. Is it the only basis? No. There's actually infinitely many other bases, but this is based on getting the RREF. This is the standard algorithm way of getting the basis. What does this mean? First of all, it means it spans the kernel. Any vector in the kernel is a linear combination of these. Secondly, it's also a linearly independent set. With two vectors, that means these are not scalar multiples of each other, and you can see that. They're not scalar multiples of each other. With two vectors, two non-zero vectors are linearly independent if and only if neither is a scalar multiple of the other. What's going on geometrically? Since this is two linearly independent vectors that's forming a basis for the kernel, that means the kernel is somehow a two-dimensional subspace of five-dimensional space. So does that mean it's a plane to the origin in 5 dimensions? Yeah, it does mean that, but we can't actually draw it, right? We have to visualize by analogy. Is that a useful thing to imagine? It does turn out to be useful in ways we'll see very strongly the last 3 weeks of the course. It turns out to be useful to imagine that. What about a basis for the image? And again, the kernel, by the way, is also the null space of A. So that would be another way to phrase the question. What about a kernel, a basis for the image? Also called the column space of A. With kernel and image, you're focused on the transformation. With null space and column space, you're focused on the matrix. But they're the same thing. What you do, the algorithm is, whichever columns you find in the REF that are pivot columns, here the first, second, and fifth columns are pivot columns where you have the leading ones. Those same columns in the original matrix form a basis for the image. So look at the first, second, and fifth columns in the original matrix. Those will form a basis for the image. Is it the only basis? No. There's infinitely many others. Is it the only basis I could get from the matrix A? Not necessarily. It's possible the first 3 columns could also be a basis. Possible. But the only thing that's guaranteed based on the algorithm, the REF, is to use the pivot columns, the columns that have the leading ones in the REF, the first, second, and fifth. That's what the algorithm guarantees. It's possible you could get other bases for the image using other columns. So I use those 3 columns, 3 4-dimensional vectors. There's the first column. Here's the second column. And here's the fifth column. Those 3 4-dimensional vectors forms a basis for the image. What does that mean? It means, again, that they span the image. Every vector that is A times X for some X can be written as a linear combination of those. It also means these are linearly independent. Why wouldn't using all 5 vectors in the original matrix form a basis? Because they're not going to be linearly independent. That's why. They're going to span. We already knew that. Every vector in the image is by definition a linear combination of these columns because of what it means to multiply A times X. But we're after sort of a minimal spanning set. That's what a basis is all about. It's finding a minimal spanning set. We can get away with 3 vectors instead of using all 5. It emphasizes that the image is a 3-dimensional subspace in 4-dimensional space. No, yeah, the codomain is 4-dimensional space. The image is somehow a 3-dimensional subspace, like ordinary space through the origin in 4-dimensional space. Can't visualize it, but you can say it. You can say those words. Is it a worthwhile thing to do? I argue yes, especially the last 3 weeks of class. It's a useful thing to imagine that. The rank nullity theorem says that if you add the dimensions of these 2 subspaces, the number of elements in a basis, 2 plus 3 equals 5, you get the number of columns of A. Well, of course, that has to be the case because the number of vectors in a basis for the kernel is the same as the number of free variables. And this one corresponds to the number of pivot columns. So it's got to be that way because the pivot columns are exactly where the free variables are not. Last thing I want to mention today is related to functions being linearly independent or not. Let's see if we can do a quick example of this. You know there are double angle formulas in trigonometry, right? There are also triple angle formulas. Oh, let's look at a triple angle formula for sine. What is sine of, I'll use t instead of theta. What does sine of 3t equals? It equals lots of different things. One thing it equals, oh, that's not bad typeset. That's bad typesetting. Let's look at this picture. One thing sine of 3 theta or 3t equals is 3 sine t minus 4 sine cube t. That's one example of a triple angle formula. Sine, I'll use t instead of theta. 3t equals 3 sine t minus 4 sine cube t. This is an identity. It's true no matter what t is. These two functions are the exact same function. If you graph them both in your calculator, you get the exact same graph. That's not obviously true, right? If you look at that, it's like, I have no idea why that's true. Well, that's because trigonometry has lots of mysterious formulas in it. Lots of mysterious identities. But it is true if we're trusting whatever this came from, Clark University. This is related to linear algebra. You could rewrite this equation in this form, sine 3t, or 1 times sine 3t, minus 3 times sine t, plus 4 times sine cube t equals 0. I'm just getting all the non-zero things on the left side. Hey, that's a linear combination of 3 functions, sine 3t, sine t, and sine cube t. The weights are 1, -3, and 4, equaling the 0 function. That's enough to say right there that these 3 functions, sine 3t, sine t, and sine cube t, are linearly dependent functions, not linearly independent, because you have a non-trivial linear combination of them giving you the 0 quote-unquote vector in this function space. What function space? Well, all continuous functions could be thought of as the function space, because these functions are certainly continuous. All differentiable functions could be thought of as the function space. These are certainly differentiable. There's lots of different function spaces you can think about here. But in whatever function space you happen to be thinking about, these 3 functions, quote unquote vectors, because this non-trivial linear combination equals 0, they are linearly dependent. And that's all you need to say. You're trusting the trig identity is true. Okay, in your homework, you have a simpler trig identity to think about and simpler functions.